Well, thanks for joining me today for this training session on issues of diesel fuel stability and fuel stabilizer solutions. I'm Eric Bjornstad with Bell Performance. And in our time together today, in this training session, we're going to review the following subjects. We are going to review the causes and mechanisms of fuel instability, including the role that composition of the fuel plays, how composition of the fuel affects the causes and mechanisms of fuel instability. We will look at fuel instability from a chemical standpoint with respect to, what are the mechanisms that change the fuel from stable to unstable. Then we will talk about outside factors that influence the stability of the fuel. And then, of course, no picture is going to be complete without considering how the fuels of today compare to the fuels of the past in this respect. And then what problems do people see in the field? And what of these problems can be linked to fuel instability as a root or contributing cause? We'll talk about how to detect and diagnose fuel stability problems. And then all of these things, it's all going to lead us to examine fuel stabilizer treatments, including, of course, Bell Performance's Dee-Zol Life. And when we consider fuel stabilizers, we want to get a good handle on what makes one stabilizer good or better than another one. So let's get started by considering how and why fuel users might have to be concerned by this concept of fuel stability. So if you think about it, if you're what we would classify as a stored fuel user, we're going to say that term a lot, stored fuel user. When we say that, what we mean is somebody who has stored fuel that uses it for something. Okay, so stored fuel users, they all have this implicit expectation that the stored fuel that they have is going to do what's expected. It's going to perform as expected at any point in the fuel's life. However, when you have unexpected fuel stability issues, and just like nobody expects the Spanish Inquisition, nobody expects instability. So unexpected fuel stability issues is basically, self-evident. When you have unexpected fuel stability issues, this leads to a number of uncertainties. This can form a number of uncertainties. For example, you might have an emergency backup system, and it runs on stored fuel. It's going to run on that to execute critical functions, like it's going to run an emergency power system that's really necessary. It's essential. If those systems fail because of fuel stability problems, that is a huge potential problem, and it happens just about every time that there's a major storm. We can also put budget uncertainty in the mix as well. Unexpected fuel problems can be particularly costly because they are unexpected. You can't account for them. You can't account for the cost of the problems they're going to bring you. How do you budget for the unexpected? I don't know. So you've got monetary costs associated with lost productivity in that kind of situation. And by monetary costs, we can talk about higher fuel usage by the equipment, of course, higher equipment costs because of the fuel not running properly, the critical costs of an impaired emergency response, if that's applicable. You've also got non-monetary costs, the mental costs, the stress of damage control and putting out fires. Consider that during significant emergencies, if you look at past precedents like Hurricane Sandy from a few years ago, typically it is not surprising that up to half of essential emergency generators do not work or do not work as needed during a major storm event. That happens almost every time, and that means you can expect that to happen for any given future major storm event that's coming up. And all of these problems, they all have a cost associated with them. And some of those costs we've already mentioned are monetary, but some of those, like we said, are non-monetary. Hits to professional status. professional status is many times more valuable to people than simple monetary factors are. People care on some level what others think about them. There's extensive social science research into the kinds of things that motivate people, and this research clearly shows that things like recognition, what people think about you, recognition can be a more powerful motivator than a simple tangible reward like a monetary bonus. And this dovetails with a second finding that research is pretty clear on. When faced with two similar choices, one is avoiding pain, the other one is seeking pleasure or getting pleasure. It's clear that psychologically people will almost always avoid the pain over seeking the pleasure. And so that's why something like impaired credibility is it's a personal cost, but it's a meaningful cost. And fuel stability problems can directly impact this when you look at someone who is in the role of being responsible for making fuel decisions. So given all this, our job at Bell Performance is to provide our customers in this arena with the right answers and also to provide them with solutions that solve these problems. So, fuel stability. The term fuel stability refers to a fuel's properties staying the same over a long period of time. It can also, another way to put it would be a substance's resistance to change over time and under various conditions. That's maybe a better way to put it. Now, like many things, petroleum, you store it for long enough, it will become it will become unstable. It will change. Why? Why does that happen? Well, because it gets exposed to certain kinds of things that initiate or help drive chemical reactions in the fuel that then change its properties, change its composition, and compromise its stability. And a fuel's reaction or lack of reaction to being around these environmental elements, that is integrally tied, or integrally, depending on if you're from the UK, is integrally tied into its composition, what it's made out of. Composition affects stability. There are a few basic things to keep in mind when you talk about petroleum fuel composition. And you always have to start at the refinery level because that's where the crude oil is turned into the middle distillate fuels and the residual fuels that we use. Now, distillate fuels, they're lighter, they have smaller molecules than residual fuels do. Examples of distillate fuels would be things that everybody knows: gasoline, diesel, kerosene, naphtha, natural gas. That's a distillate fuel too. Residual fuels is all the stuff that's left over after the distillates are gone, namely heavy fuel oil and then asphalt and tar. So these fuels that we refine from petroleum, they're coming from a natural source, and so they are complex mixtures of hydrocarbons of all different shapes and sizes. And when you consider that, that leads us to the fourth point, which is no two fuel samples are exactly the same because they are a natural product. There's always variation in the exact composition between crude oil that's pulled out of the ground in Pennsylvania versus crude oil that came from the North Sea or Venezuela. It's crude oil, but it can be markedly different. So as you can see, this is a simplified schematic. We call it the simplified refinery. Now, as you can see, the area that you see circled is where it's supposed to represent the area where some critical things happen with respect to what they're doing to the fuel. So you have a distillation column, and it is used to essentially distill, break apart, split even the crude oil into its components. Now, each barrel of crude, every 42 gallons, typically yields the same amount of proportions of certain things. Typically about 42% gasoline, 22% diesel. And by diesel, we're talking about on-road diesel. So almost two-thirds of it is that gasoline and that diesel. Then you've got jet fuel. You've got fuel oil. Liquefied petroleum gases. Jet fuel is 9%, fuel oil is 5%, liquefied petroleum gases is 4%. There's other products like naphtha, which is 18%. When you add all these things together, you're getting the distillate fuels is about 93%, and then 7% is the residual leftovers. And apart from the really simple fuels like LPG, methane, or propane, all the gases, these fuels are composed of mixtures of hydrocarbon molecules. You got alkanes and you got alkenes. Alkanes are single bonded. Alkenes are double bonded. And you've also got carbon rings and you've got paraffin molecules and stuff like that. So we've said all this to lead into an actual point here. When you're talking about molecular composition is important when we start to consider the processes that are involved in the real world with fuel instability versus fuel stability. So, at its heart, the development of fuel instability, or the loss of stability in fuel, at its heart is a chemistry problem that involves the chemical conversion of precursor molecules into molecules of higher molecular weight. In other words, bigger and heavier molecules that have limited solubility. In other words, they're more likely to drop out of the fuel. See, all fuel starts with a certain number of unstable molecules already in the fuel, and they float around in the fuel, and because they're unstable, they're always looking for other things to react with, because that's just the nature of how chemistry works. Unstable molecules look to become stable. Now, over time, they will find things to react with. And then the fuel will get exposed to catalytic elements that cause the reactions to either start more quickly or happen more easily. And so over time, normally stable hydrocarbon molecules in the oil or in the fuel, they're transformed into unstable precursors of chain reactions that eventually, given enough time, they compromise the stability of the fuel. So why does fuel become unstable? Why does fuel darken, and why does it stratify, so to speak? It does these things because the long polymer molecules that have been created by these chemical chain reactions eventually become too big and too heavy to stay dissolved in the fuel. So we know that fuel instability is a result of chain reactions that chemically alter the molecular precursors and change them and other molecules into heavier compounds that then aggregate together and drop out of solution with the fuel. Now, fuel at its heart is an organic liquid that has certain unstable elements that, given enough time, cause it to go bad. Now, a fuel supplier will always aim to sell the highest quality fuel possible. However, because of certain circumstances, fuel may be on the way to being aged. It may have undergone some oxidation. It may contain water. It may have been contaminated in some way before it was even delivered to you, or even before it got to the vendor themselves. See, fuel has to travel first from the refinery, then to the terminal, and then to the end user destination. And on its way there, through that distribution system, it goes through pipelines. It may go into a barge. It can be trucked, and it's going to sit in various storage tanks. And along the way, you're going to have changes in temperature. You're going to have exposure to atmospheric oxygen and water. Exposure to a lot of different things in a lot of different places. And so as a result, fuel quality diminishes over time, no matter how fresh the fuel started out. And then when the fuel is finally used, it's exposed to the heat and the pressure of the engine injection systems and centrifuges and, pumps and heaters and all that stuff. And so you get asphaltene agglomerations, which can, negatively affect combustion efficiency, can affect emissions. So all of these things together lead us to consider that there are certain things out there that when the fuel is exposed to them, they can be shown to speed up the rate at which fuel becomes unstable. Those things are the ones that you see on your screen: water, oxygen, certain metallic catalytic metal, metallic catalysts like copper and brass. All of those things make it easier for instability reactions to happen. But those aren't the only thing. You've also got heat and light, and you've also got exposure to microbes. This last one's a big one because microbes, they feed off of certain elements in the fuel, but then they also produce acids, they produce peroxides and byproducts that, over time, destroy and compromise stored fuel quality. So, exposure to one or more of these things usually results in the formation and the expansion of unstable molecular precursors in the fuel. So what do these precursors do once they are present? Well, we've already mentioned it to a certain extent. If they're unstable, they will seek to react with other molecules, and the result is that you get a longer polymer string when those two molecules react and combine. And the longer those molecules get, the more mass they have, the heavier they become, and the more unstable they become. So the fuel becomes unstable when the heavier components that previously were, dissolved in the fuel, it becomes unstable when those components can no longer stay dissolved in the fuel because they've been reacting with other things. And that's what we start to see when we have the formation of sludge or varnishes or gums or shellacs or, whatever you want to call them. Now, from a practical standpoint, we are all familiar with the effects that this kind of thing has on the end user. I mean, think about it. If you try to burn darkened fuel, what kinds of things are going to happen? Well, the fuel's not going to burn as well in the engine, so it's not going to get as much mileage. You're going to have poor performance of the engine. You'll start to form deposits in, the fuel injectors, combustion chambers. You'll get more black smoke, especially the particulate, the PM emissions that can affect diesel particulate filter regeneration. So these are all serious enough effects for users to be concerned about this kind of thing. Now, there may be more experienced people out in the industry who have lived through a lot of changes, and they might wonder why we have to be so concerned now about this issue, because they can remember a time when things were more than a little different. That basically begs the question, why is fuel different? Why is it a problem now? Well, we have alluded to this a little bit a couple slides ago. We talked about the fact that now when you're splitting crude oil and you're refining crude oil, you get about 93% distillate and 7% residual. Now, before, let's say in the 60s, and let's say 1970. 1970 was a completely different picture. 1970, it was more like half and half. You have about 54% what they call distillate fuel straight run. That means the gasoline and the diesel and the jet fuel and stuff like that, the distillate fuels. You had about 54% of those, and then 46% of it was the residual. Got residual tar is what we've got on there. But what happened was that since they started having cracking processes, implementing cracking processes in the refinery, and that enabled them to get a lot more distilled fuel, the catalytically cracked distilled fuel. So those cracking processes, while on the one hand they're good because you can make more gas and diesel, unfortunately the gas and diesel that you do make is more unstable because it's got more double bonds in it and it has more unstable molecules. Now another factor is ULSD, ultra low sulfur diesel. In the past, if you've ever seen references or explanations of this, we talked about the fact that when they remove sulfur at the refinery and they do stuff like hydrotreating, and that changes the fuel chemically. It removes some of the paraffin. It removes, or they've limited aromatic content. And, of course, they've taken a lot of the sulfur out. And so the long and short of it is that fuel attracts water more easily. It also has much less resistance to microbes. And microbes, so the microbes see ULSD and they have a party because they will live and they will thrive in ULSD and they will make it go bad a lot faster than it used to be. How much faster? Um, 40 years ago, you could expect to get 3 to 5 years easy out of stored diesel fuel. Now, if you don't treat it, if you don't do preventive maintenance, less than a year is very typical for untreated diesel fuel shelf life. So fuel does not last as long as it used to. If you have stored fuel, how can you tell? How do you know if it is bad or not? Well, initially, you can do something as simple as drawing a fuel sample and examining it just on a sensory level. I mean, what does it look like? It sounds simple enough, but you would be surprised at the number of storage tanks out there that are filled with fuel that have been sitting there for years, never having been checked by a human person. They're essentially out of sight, out of mind. So you take a fuel sample and you look at it. Does it look like it's supposed to? Does it smell like it's supposed to? If the fuel has darkened and gone bad, well, you're going to see that it's darkened. And if it's got microbial infestation, many times you can see, biomass formation. You can smell that something is, it doesn't smell like fuel's supposed to smell. So something as simple as that can even give you some kind of idea if the fuel has gone bad. So it's a simple yet very valuable thing to do. But, while these things are useful, sometimes these sensory tests alone are not quite enough by themselves. That means you need to start looking at quantitative testing, ASTM testing. Many times we need more specific answers to this question than just, what does the fuel look and smell like? So we use ASTM testing to quantify or measure the extent to which a fuel has gone bad, or even to just give us a heads up on that a fuel sample may be close to being on its way out, so to speak. Now, one thing to point out here is that when you're talking about the gamut of ASTM tests, some tests are predictive and some tests are descriptive. A predictive test tells you a slightly different kind of thing than a descriptive test tells you. Now, a descriptive test could be, an example of that could be like a water and sediment test. Water and sediment test tells you the actual content of water and sediment that are present in a fuel sample. It is descriptive of the present actual state of the fuel sample. Okay, so that's easy enough. In contrast, if you're doing a stability test, like an oxidative stability test, D2272, the very nature of the term stability is predictive because the definition of stability is how well something resists change. And if you think about it, that is a predictive consideration. What is likely to happen to the fuel, or what condition is the fuel likely to be in the future? So these kind of stability tests that you can run, like an oxidative or a thermal stability, or what they would call the petrooxy test, which is starting to become spec'd in for ultra-low sulfur diesel fuels. These kind of stability tests, they don't tell us, what percentage of the fuel is this way, or they don't tell us, the composition of the fuel, something like that. That would be a descriptive test. A stability test tries to give us a numerical representation of the present condition of the fuel, but with respect to predicting whether that condition of the fuel is going to change over time, what will happen in the future. That is what stability is. Think about it a different way for those of us who are sports fans. Let's use a different example. Let's talk about the NFL quarterback. Now, let's say that we were looking at NFL teams, and all 32 NFL teams, and their quarterback situations. And we were commenting or trying to assess the stability of a team's quarterback situation. Now, we could give every team in the NFL a rating on what we think we know about their stability at quarterback. Now, if we do that for the Packers, or we do that for the Patriots, the Packers have Aaron Rodgers, the Patriots have Tom Brady. If you give the Packers a stability rating for the quarterback situation, when you do that, you're not describing how big Aaron Rodgers is. When you give the Patriots a quarterback stability rating, you're not describing any of Tom Brady's physical characteristics or how far he can throw or anything like that. If we did that, those would be descriptive things, but we're not doing that. We are predicting or describing the likelihood that the team's quarterback situation will change at some point in the given near future. We are describing how stable their quarterback situation in that respect. And everyone knows that the Patriots, their quarterback situation is highly stable. Tom Brady is not leaving anytime soon. Contrast, you have like the Cleveland Browns. They have poor quarterback stability. It's very likely that their quarterback at the end of the season is going to be different than what it is right now, at least in 2018, which is what we're talking about here. They just drafted a quarterback with the first pick in the draft. Maybe he turns out to be the greatest one that's ever known. So if you're watching this in 5 years and Baker Mayfield is a perennial All-Pro, then please forgive our lack of foresight here. So anyway, relating all this back to fuel, there are a couple of predictive stability tests that you can run on fuel. There's actually 3 of them. First one, D-2272. That's oxidative stability, what they call accelerated oxidative stability. It describes the stability of the fuel upon long-term exposure to oxygen. Now, the one below it, D-3241, that's accelerated thermal stability, which speaks more to predicting what will happen with the condition of the fuel as it is exposed to elevated temperature over a long period of time. Now, both of these tests are labeled accelerated because their test methods cause them to try to speed up the processes that normally at ambient temperature would take a long time to unfold, because you want to have a reliable answer as quickly as possible. Now, laboratory tests like these are essential to giving a more defined snapshot of the fuel's condition at any one point in time. And so they give you very valuable information on not just whether a fuel meets a standard, but also how close it is to failure or not. Now, I said just a minute ago that there are 3 tests. The first 2 we mentioned, oxidative stability and thermal stability. The third one, which is not on your screen, is called the petrooxy test. And it is basically very similar to oxidative stability, tells you the same thing, but it's just optimized a little differently to be, shall we say, more accurate in ultra-low sulfur diesel fuels. So, using these accelerated stability tests is the only way to quantitatively predict additive effectiveness in a specific fuel batch. What we mean is, if you have reason to believe that the fuel is unstable, or you want to keep it from going unstable, rather, that's a better rationale. You want to keep it from going unstable. You add a fuel stabilizer. Then you do a stability test, and it can tell you how much that stabilizer has improved the stability rating for that fuel. So, up to this point, we know how fuel goes bad. We know the causes of fuel instability and the process by which it happens, at least on a cursory level. We know how to more definitively assess a fuel's condition in this regard. So the question now is, how can you protect fuel from becoming unstable in storage? What are the preventive best practices with respect to fuel instability? Well, since you cannot completely protect any fuel from exposure to environmental bad actors, remember, oxygen, water, microbes, heat, light, catalytic metals, those things, as complete protection from environmental bad actors is not, that's not feasible. You can't expect to be able to do that. The only way that you can protect fuel quality and storage is you have to treat the fuel with a stabilizer to prevent the reactions from starting in the first place. And that brings us to the stability solutions that Bell Performance offers, which is Dee-Zol Life, fuel stabilizer and antioxidant. The only way to mitigate fuel instability is to stop the chemical reactions or interrupt them in the beginning so they never have a chance to initiate a chain reaction. Then that means that you need to have a fuel stabilizer treatment present in the fuel in the beginning. So Bell Performance offers Dee-Zol Life as its fuel stabilizer package. Now, this is by no means to imply that it's the only one out on the market. I mean, if you know anything about this kind of thing, you know that there are many fuel stabilizers or things that market themselves as fuel stabilizers. But we also know that they are not all the same, and there are substantive differences between different options for stabilization. And so if you are an operations manager, or if you're in charge of some fuel, the logical question here is, well, how can I tell one from the other if they all claim great things for themselves? Well, let's unpack that a little in a little bit more detail. Now, the need for stability average varies from one fuel to another. The need depends on how the fuel was made, the crude oil source, the refinery processing, and the blending. But by and large, stability additives, they work by blocking one step of a multi-step reaction pathway. Because the chemistry of this whole thing can be fairly complex, an additive that is effective in one kind of fuel may not work exactly the same in another, unless the stability package contains all the different types of active ingredients that address the major pathways or the most common pathways of fuel instability and degradation, which means we need to talk about those because Bell Performance's Dee-Zol Life does contain or address all of these major pathways. So what are they? These are the types of stability components that when you put them together, they comprise what we would consider a best practice stabilizer for petroleum fuel. First one, antioxidants. Now, you see antioxidants, and then in parentheses you have 10 to 80 parts per million. One aspect, I should say a major aspect of fuel instability is oxidation. That's when oxygen reacts with reactive components in the fuel, which then creates or sets off complex chain reactions. So an antioxidant works by stopping or interrupting these chain reactions so that they don't really get started. And now the 10 to 80 ppm means that these are typically in formulations, they end up in the fuel at an effective treat rate of 10 to 80 ppm. An effective treat rate is terminology that's used that basically means once you use something at a given treat rate, how much of the active ingredient actually is in the fuel when it's all said and done. So antioxidants is the first one. Second one is what we would call stabilizers. Now, you may say, well, we're talking about stabilizers, so, what's the difference? Well, what we're really talking about here, we're actually talking about acid-base stabilizers or acid-base neutralizers. Acid-base chemical reactions are another, along with oxidation reactions, those are another kind of reaction that can happen while the fuel is going unstable. So you have essentially it's like an acid neutralizer or a base neutralizer. They are stabilizer compounds that stop these reactions from happening. Typically, they tend to err towards being basic amines, which means that they really attack the acid part more than the base does, because the acid part is really the more common aspect of this kind of thing. And they're typically present at an effective treat rate of 50 to 150 ppm. So they react with acidic components that may form in the fuel, and they tend to form, the products of their reactions remain dissolved in the fuel, but they're non-reactive. So that stabilizer is essentially stopped further degradation of the fuel in that way. Third one, metal deactivators. Metal deactivators typically present between 1 and 15 ppm. When you have trace amounts of certain metals that a fuel may be exposed to, such as copper or iron, those can catalyze reactions that lead to fuel instability. So you have a metal deactivator that actually ties up the metals and neutralizes their catalytic effect. Fourth one, dispersant. Dispersants don't actually stop chemical reactions from happening, but what it does is it takes the particulates, the heavy end molecules that are formed from these reactions, and it actually keeps them dispersed in the fuel and keeps them from clustering together or forming larger molecules. And so that essentially extends the working life of the fuel, because one of the things that can cause instability to speed up is if these reaction byproducts happen to bump into each other and react and form larger and larger molecules. So a dispersant will help keep that from happening. And then you have fifth one, corrosion inhibitor. Again, present in relatively small amount, only 5 to 15 parts per million. And see, most petroleum pipes and tanks in the distribution system, most of them, they're not made out of fiberglass, they're made out of steel. And if you get water in there, you can very easily get corrosion. And over time, that can cause serious problems with that tank and also with the fuel. So a corrosion inhibitor many times will be in a fuel stabilizer package, and it will be like a filming, well, some of them are filming amines, some of them are amide components, but the basic way they work is that they migrate the metal surfaces, and they actually attach the metal surfaces, and they form a barrier, a physical barrier that protects that surface from attack by corrosive agents. So those are all 5 of those things are important to have in a fuel stabilizer package. The best stability treatments, like Dee-Zol Life, will contain all 5 of those. Now, when we were talking about those 5 things, you notice when we were talking about them, we had metal deactivators, 1 to 15 ppm, dispersants, 15 to 100 ppm. There's a reason why we put that information on there. There are many treatments out there, multifunction treatments, and a lot of them will claim some aspect of stability, fuel stabilization as one of the benefits. Many times it will be one of a whole laundry list of benefits that it lists, and invariably it will say it does all of these things at some really low tree rate, like 1 to 5,000 or 1 to 10,000, or we've seen some that are even higher than that. Now, excuse me, the problem here is that if you know that you have to have certain things in a formulation in order for it to actually do a given claim, and if you add up the required concentrations that you know that you would need, you start to realize, first of all, that there's a minimum amount of formula space that's necessary in order to put together an effective treatment. And if you have, let's say, a product that claims to do 7 different things, and all you have to do is add 1 to 10,000, most likely it's not going to have enough active ingredients in it to do anything, including stabilizer, because there's just not enough of it as ends up in the fuel for there to be enough of those things necessary for them to do what they need to do. For example, let's say you have something that says you can do everything at 1 to 10,000. That's 100 parts per million in the fuel. But you saw that even if it was claiming to be a stabilizer, remember that you need at least 80 ppm of the acid-base neutralizing stabilizer component for it to do anything. And you've only got 100 ppm of formula space. So where are you going to put all the other stuff? See what I mean? So transition back to Dee-Zol Life. Dee-Zol Life, we said that it has all of those things present in it. its tree rate is 1 to 2,000, which means it has enough formula space in it to deliver all of the important active ingredients in the right amounts to accomplish all of those essential tasks of fuel stabilization. So that is what Dee-Zol Life does. Now, let's address some questions that people typically have about it. And these are important questions to have, especially some version of this. How much will Dee-Zol Life extend fuel life? This is a fair question, of course, and one that's asked in some form or another pretty commonly in the marketplace. People have a right to know what to expect if they're going to use a product. Now, remember first that there are differences in fuel sample properties and storage conditions that can change the answer. So in reality, there is no one answer that is right in every situation because their fuel samples differ in composition. Even fuel samples coming from the same refinery, there are different storage conditions that can change the what happens in one fuel sample over the other. However, telling people it depends does not necessarily satisfy them because they still need to have something to frame their expectations on. So that means we have to give them some kind of answer. So what we typically say is, in most fuel samples, all other things being equal, you can extend stored fuel life by at least 2x. 2 to 3, sometimes 3 to 4, depends, but that is kind of the baseline answer that we would give to something like this. This is another question that we get. Reversing bad fuel. I've got fuel that's already gone unstable. Can I use Dee-Zol Life to turn it back to the way it was? Well, the short answer is there's no feasible way to reverse fuel that has progressed to the point where its heavy ends are no longer soluble. In other words, you cannot put Humpty Dumpty back together again. However, there are feasible options for treating that unstable fuel to make it more usable, so to speak. So if you add fuel stabilizer to an unstable fuel, it's not going to put Humpty Dumpty back together again, so to speak, but it will keep it from becoming further unstable or more unstable. And this is important because it also addresses the person who thinks that the fuel is fresh, is in great condition. It will help that as well, but it will help bad stratified fuel. It will help keep that from getting worse, essentially. So what would you do with fuel like that? Well, there are certain options. I mean, you would add stabilizer first, but then, I mean, you would try fuel filtration to try and remove some of those heavy ends, and then you would probably add cetane improver, possibly even some kind of combustion catalyst to try and help burn the fuel off as cleanly as possible. You could also use a sludge dispersant like SDF, which would help to dissolve and solvate some of those insolubles back into the fuel. So as with many types of treatments, fuel stabilizer works best if it's applied properly. What does that mean? Well, the effectiveness of a fuel stabilizer depends on how well it's mixed into the fuel at the right time. Dee-Zol Life should be applied to the fuel as early in its life as possible. It must be applied to the fuel when it is fresh, before precursors have been allowed to form, or before the existing precursors are really starting to react with other things. Then after you apply it, you want to circulate the fuel. So fuel circulation is always recommended because proper mixing is extremely important. For some large bulk fuel users, they would probably use direct injection, where the fuel's being pumped into the storage tank, and they would inject the stabilizer into the fuel line. That is an excellent way to do it as well. And so that brings us to the conclusion of this training on Dee-Zol stabilizers. Hopefully, it will become clear that Dee-Zol stabilizers are extremely important. We could say that they are an essential tool in good fuel preventive maintenance. Now, If you have any questions about this, my email's up on the screen, ebjornstad@belperformance.net. You can email them to me. Just let me know that you have a question about the fuel stabilizer training. I will be glad to help in whatever way that I can. So thanks for joining me today, and I will see you next time.